For our fourth video in chapter 9, we're going to talk about stoichiometry, a neat little trick that gases allow us to do. Then we're going to talk about effusion and diffusion. Okay? But please note, in chapter 9, I am skipping the wet gases part of section 9.3, collecting a gas over water and doing calculations with vapor pressure. We're going to save those for later and omit them from chapter 9 right now. So let's get into stoichiometry. Okay. Now, we first learned stoichiometry in chapter 4, right? And we worked with reactants, we worked with products, and a gas could be either. Now, we've seen in previous videos, the ideal gas law, right, relates pressure, volume, temperature, and moles. Okay? So we can use the ideal gas law with a balanced chemical equation, right? Stoichiometry tells us moles of things, and then we can use that if we're dealing with a gas to find anything else, pressure, volume, or temperature. Okay? But what's unique about gases is something that's known as the volume ratio. Okay? If we are assuming ideal gas behavior, okay, the volume ratio of any two gases in a reaction, provided we don't change the temperature or the pressure when that reaction undergoes, right? The ratio of the volumes is the same as the ratio of the moles in our balanced chemical equation. So the volume ratio is the same as the stoichiometric ratio. That's because if temperature and pressure are constant, right, volume is proportional to molar amount. We saw that earlier in Avogadro's law. Okay, so volume is directly proportional to moles of a gas. So if I have a balanced chemical equation, like I have down here, right, nitrogen and hydrogen coming together to form 2 ammonia, then the ratio of the moles in the atoms is the same as the ratio of the volume. So 1 mole of N2 combines with 3 moles of H2. With gases, I can think about it a different way. 1 liter of N2 combines with 3 liters of H2. So that's the volume ratio, a nice little trick with gases. Okay, but remember, before we work with moles, right, before we change other values, we have to be working in moles. That's what stoichiometry is all about. Remember, we got to go over the molehill. Okay? So if I'm given a mass to start with, for example, to do stoichiometry, I first have to convert moles, then use that moles to find moles of anything else, provided I have a balanced chemical equation. And then the ideal gas law, PV equals nRT, would allow me to find any other quantity for a gas specifically. Okay. Here we have another example problem hidden in the slides, right? And you can look for a supplementary video to show the answer to example 9.15. If you want to pause and give this one an answer on your own, the final answer should be 1.87 atmospheres. So that's stoichiometry. Let's talk about effusion and diffusion of gases. Okay. Everybody should be familiar with the fact that gases spread readily throughout a container. Right? If you had a closed container of a poison gas, you wouldn't just set it on the table in front of you, open it up, and be calm, right? Because gases spread throughout their container. Okay. And as a gas molecule moves, it doesn't have to worry just about colliding with the walls of whatever it's in. It also has to worry about colliding with other gas molecules. Okay. So we can talk about gases in terms of something that's known as their mean free path. The average distance a molecule travels between collisions. And the mean free path increases as I decrease the pressure. Or a different way to say that is that mean free path and pressure are inversely related. Because as I decrease the pressure, right, and allow things to spread out, that means that they have more space to diffuse. Okay. And that brings us to diffusion. Diffusion is the process by which molecules disperse in space. Okay. And they always do that in response to differences in concentration. Because really, we can't control the way any molecule as a gas will move, right? It's a random motion. So it's all about concentration as we're thinking about diffusion. So let's talk about how that process of diffusion occurs. Well, if I have 2 different gases that don't react with one another, hydrogen and oxygen in this case, a valve in between the 2, well, it's blocking. They can't do anything, right? But when I open the valve, they can start to spread out. and they do so until they've reached the same concentration on both sides. But we can do calculations with diffusion. Right? We can calculate rate of diffusion. Just like any other rate, we'll talk about rates a lot in Chem 2. Okay? Rate of diffusion is the amount of gas that passes through an area per unit time. So for diffusion to occur, we have to have two different concentrations, two different gradients. And our rate depends on what those concentration gradients are, right? Is it 45-55? Is it 90-10? Is it 100-0? Right? The difference in the concentration gradient will affect the rate of diffusion. So will the surface area available, right? How wide is that opening in the middle, for example, and the distance that the gas has to travel. Right? So as you increase the concentration gradient, you increase the rate of diffusion. As you increase the surface area, you increase the rate of diffusion. If you increase the distance the gas has to travel before it can diffuse, then you decrease the rate. Okay. So now we have another idea, effusion. Effusion is specifically dealing with a vacuum. Now, escape of gas molecules through a tiny hole into a vacuum. Similar to diffusion, but we don't have two different concentrations. We're going into a vacuum. Okay? So here we see effusion, for example. Purple molecules going through a small hole. And we can also calculate how things effuse using Graham's law of effusion. Okay? Tells us that the rate of effusion of a gas is inversely proportional to the square root of the molar mass of the particles. So rate of effusion is proportional to 1 over the square root of the molar mass. Or if I'm directly comparing two things, right, the rate of effusion of molecule A over the rate of effusion of molecule B is equal to the square root of, notice they flip now, molar mass of B over the molar mass of A. Okay. So you can do calculations with that. You'll have one on your sapling. All right, this is what those two ideas look like as a picture. You can do the calculations, right? Hydrogen to the ratio of oxygen, which effuses faster. What you should focus on with effusion and diffusion is knowing that lighter molecules, things with smaller molar masses, effuse faster. Okay. So you can do this calculation, right? Hydrogen, because it's lighter than oxygen, effuses 4 times faster, right? The ratio is 4-to-1 for the final answer here. But conceptually, from this video, know and be familiar with the fact that lighter molecules effuse faster. Okay? Know the 3 factors that affect rates of diffusion, and know the volume ratio trick that you can use for stoichiometry.